Section 5.7 is the binomial theorem. I can expand a binomial using Pascal's triangle, and I can use the binomial theorem. Big ideas here. There are three ways to expand binomials. We can use the distributive property, Pascal's triangle, and the binomial theorem. The distributive property can get pretty messy the higher the exponent is on our binomial. So using Pascal's trial and the binomial theorem, which are actually very similar, the binomial theorem just lets us apply Pascal's triangle to more complex binomials. That's going to be more beneficial when we get to higher degree binomials here. A pattern of coefficients, and the pattern here can be used to write the expansion of a plus b to the nth power. So this looks like a lot, guys, but all they're telling us is we're going to start off with a to the nth power, and as we move left to right, it's going to decrease by 1. We're also from the right going to start off with b to the nth power, and as we move left, decrease by 1 every time. And then we use our coefficients from Pascal's triangle. So to expand the power of binomial in general, we're going to first multiply as needed, then write the polynomial in standard form. That's important here. I would recommend that you write it in standard form to start with. So if you have something like b plus a to the 4th power, I would rewrite my binomial in standard form, alphabetical, a plus b to the 4th power, before I expand it, because here we only have to move 2 pieces instead of moving the entire function. So again, remember, in standard form, they need to be alphabetical, and they need to be highest degree to smallest degree of our variables. So if we have an a and a b, for example, it's our a value that has to be the highest degree to the lowest degree, because a is first alphabetically. On the bottom of page 326, they took a plus b and expanded it. They took a plus b and then a plus b squared and then a plus b cubed, a plus b to the 4th. And what you can see there is that the coefficients of the expansion match up with the numbers of Pascal's triangle, which I have here. The first and last numbers in each row are 1, and the other numbers in the row are the sum of the 2 numbers above it. So for the 7th power, for example, if we had a plus b to the 7th power, we would use the row with 1, 7. N's are both going to be 1. And to get the numbers in between, we take the row above it. 1 plus 6 gives me 7. 6 plus 15 gives me 21. 15 plus 20 gives me 35. 20 plus 15 gives me 35. 15 plus 6 gives me 21. 6 plus 1 gives me 7. And again, 1's on the ends. Each row is going to be a palindrome, meaning it's the same forward as backwards. So that's something to look for, especially if you have to expand here. So if we wanted the 17th, remember we put a 1. We'd add these. We'd add these, and so on, and eventually end with a 1. Okay, so for the expansion of a plus b to the 6th power, we're going to use Pascal's triangle here. We want to the 6th power, so we're going to match that here with our 6th row. 1, 6, it's actually our 7th row, but the one with the 6 in it is what we're looking for. Okay, 6 is our second number. So my coefficients I'm going to write down first. I'm going to give each one of them a column. 6, 15, 20, 15, 6, 1. I want to space them out as best I can so I can make sure I see where my columns are so that they fit there. Now, I'm going to take whatever's on my right side of my binomial and start it on the right side. So b to the 6th power. It gets the exponent from outside. Then we subtract 1 as we move over. 5, 4, 3, 2, 1, and eventually none. We're only ever going to have one empty spot. Okay, on the left side, I start on the left. A to the 6th, a to the 5th, a to the 4th, a cubed, a squared, a, and none. So each column gets one term from each of the left and the right monomials in my binomial. Okay, the one on the right starts on the right, the one on the left starts on the left. Now we're going to multiply each of these columns together, and that's going to give me a term in my final polynomial. So here I get 1a to the 6th. All three of these I multiply together, plus 6a to the 5th b, and remember we want them in standard form, so alphabetical, plus 15a to the 4th b squared. And again, remember I got those by just subtracting one from my exponent as I moved left to right, depending on which way I was going and where I started. Plus 20 a cubed b cubed plus 15 a squared b to the 4th plus 6a b to the 5th plus b to the 6th. So this right here is the polynomial I get when I use Pascal's triangle to expand a plus b to the 6th power. I also could have done that by taking a plus b times a plus b times a plus b times itself, exponent number of times. I could have foiled and foiled and foiled and then distributed those into each other, but that gets to be a lot of stuff to do. So using Pascal's triangle here is very helpful. Take note on page 327 deals with the binomial theorem. The binomial theorem lets us apply Pascal's triangle to expansions with any linear factors. So the thing here to remember is the binomial theorem is pretty much the same as Pascal's triangle. It's just we can apply it to more things. So rather than just having a plus b to a power or d minus 3 to a power, okay, we can use 3x and negative 2 as our a and b factors. It's still going to work the same way. So we're going to start off with our exponent. That's going to give us our coefficient. Here it's 5, so I look at the 1, 5 row of Pascal's triangle, and I get 1, 5, 10, 10, 5, 1 as my coefficients. Again, remember that my exponent is going to match my second numbers in on both sides. Now, starting from the left, I have a 3x. So I'm going to start at the left. 3x to the 5th power. It matches my exponent. As I move over columns, I subtract 1 from that exponent. So every time it gets just a little bit smaller. To the 1st power, and then I don't have any. Again, we only ever have that one gap spot. Negative 2, since it's on the left side, I start on the left. Sorry, on the right side, I start on the right. And I take it with the exponent of 5. Negative 2 to the 4th. Negative 2 to the 3rd. Negative 2 squared, negative 2 to the 1st, and then I have none. Now, we're going to multiply together each of our columns. When we do that, we have to be careful here. Okay, when I multiply this column, keep in mind we have to distribute that exponent. It's actually 3 to the 5th power, x to the 5th power. So this is 243 times 1, 243 x to the 5th. 3 to the 4th is 81 times negative 2 times 5. Don't forget to multiply your coefficient in there, which gives me negative 810 x to the 4th. And again, that's because the 4 exponent goes to both the 3 and the x. My third column here, 3 cubed is 27, x cubed, negative 2 squared is 4, times 10 gives me 1080 x cubed. Remember that exponent goes to both my 3 and my x. Here, 3 squared is 9. I still have x squared and negative 8. So I multiply those out and I get minus 720 x squared. Negative 2 to the 4th power is 16 times 3 times 5. Gives me positive 240, and I still have an x. And my last column is 1 times negative 32, which is just minus 32. Here is my polynomial. A couple things to keep in mind. Expanding binomials has a lot of patterns to it. Our signs, if it's positive, are always going to be positive. If we're subtracting in our binomial, our signs are going to alternate. Positive, negative, positive, negative, positive, negative. Okay, it might start negative, positive, negative, positive. It might end positive. That all depends on our exponent, but they will alternate. Also, our variable exponents are going to have a pattern as well. 5, 4, 3, 2, 1. It may not always be going down by 1. It depends on what we start off with. If we start off with x cubed, for example, inside, then we'd have had 15, 12, 9, 6, 3, and none. So our pattern is going to be the same throughout. It just might not always be going down by 1. So keep in mind that's something to look for just to make sure. Are my signs alternating? If it's subtraction, if it's addition, they should all be the same, all positive. And my variables should have a pattern. Now, feel free to pause here and give this a try if you'd like. Again, our first step is to figure out what our coefficients are going to be, and that comes from my exponent. Here my exponent is a 4, so I'm going to use the row on Pascal's triangle that is 1, 4. The rest of it is 6, 4, 1. We should always have one extra coefficient or one extra column than our exponent. So if it was to the 12th power, we'd have 13 coefficients, for example. Here we have 5 coefficients because it's to the 4th power. Now, starting from the left, I have a 2x. Since it's on the left side, I start on the left side to the 4th power. I go all the way across, keeping that exactly the way that it is, that first monomial, and I just subtract 1 from my exponent as I go. And my last column, I have none. On the right side, I have -3. So I'm going to start on the right, -3 to the 4th power. And as I go to the left, I subtract 1 from my exponent each time, eventually getting none. Now I'm going to multiply my columns together. The entire column. Keep in mind that exponent goes to both pieces. So 2 to the 4th power is 16. X to the 4th. Here I have 2 cubed, which is 8x cubed. So I take 8 times -3 times 4, and I get -96 x cubed. Here I take 2 squared and get 4x squared. -3 squared and get 9. So 9 times 4 times 16. It's going to give me 216x squared. Still have that x squared here. -3 cubed is -27 times 2 times 4. It's going to give me -216. Just have one x here. And in my last column, I take -3 to the 4th power, which is 81, times 1, and get +81. And that is my polynomial, or my binomial expanded as a polynomial in standard form. Again, we want to check, do we have our patterns? Okay, well, positive, negative, positive, negative, positive, perfect, since we were subtracting. And my exponents should have a power, or a pattern on my variables. 4, 3, 2, 1. The only other thing I want to point out here is on a problem like 39. Here, exponent is 6, so my columns coefficients are 1, 6, 15, 20, 15, 6, 1. On the left side, I have 4x cubed. That's what I have every time. My exponent is 6, so that's what's going to change, is the exponent on my binomial. Same thing starting from the right. I have -2y squared to the 6th power, because that's the exponent on my binomial. -2y squared to the 5th power. My -2y squared stays the same every time. It's my outside exponent that changes. So that, and I want to show you how the exponents work here. I'm just going to do one column. I'm going to take 20. 4 gets cubed, and the x cubed gets cubed. -2 gets cubed, and the y squared gets cubed. I take that into all the pieces on both of them. Power to a power means my exponents are multiplied. My exponents are multiplied on my variables. So here I have -8, 64 times 20. which gives me negative 10,240 x to the 9th y to the 6th. And that's